That sounds impossible, contradictory, almost careless, because by definition, nothing can be older than the universe. Time itself begins at the Big Bang. No before, no earlier chapter, no prologue, and yet the story is not that simple. When we talk about age, we assume time flows the same way for everything. We assume duration accumulates uniformly. We imagine the universe as a stopwatch that started 8 billion years ago, and has been ticking ever since. But the universe does not carry a single master clock. Clocks tick differently depending on motion. Diffferently, why parasol rayed against the ast on Relativity, and when we reach the ultimate boundary of physics, the speed of light, something dramatic happens. Time disappears. For anything with mass, time is unavoidable. You age. You accumulate seconds. You march forward whether you like it or not. But light is not like you. Light does not experience time the way matter does. Along its path through spacetime, the proper time, the internal measure of duration, is zero. Zero? So imagine the earliest light ever released. Photons born when the universe first became transparent, when matter and radiation parted ways. That ancient radiation still fills the cosmos today. We call it the cosmic microwave background, the afterglow of the primordial fireball. From our perspective, that light has been traveling for 8 billion years, but along its own path. No time has passed. The moment it was emitted, and the moment it strikes a detector, are connected by a light-like interval, with no internal duration. In a very precise geometric sense, the photon has not aged. So when you hold a detector to the sky and measure that ancient radiation, you are touching something that, in its own description, has not moved forward in time at all. It was born at the dawn of the universe. It reaches you now, and along its world line, those events are adjacent. What, then, does older even mean? If age is measured by accumulated proper time, and light accumulates none, can we call it young? Can we call it ancient? Or does it sit outside that language altogether? The phrase, light older than the universe, sounds absurd until you realize that our notion of age depends on clocks that do not apply at the cosmic boundary. Time began with the universe, yes, but time does not behave uniformly within it. And when we examine the oldest light in existence, we confront a radical possibility that the fabric of spacetime connects the beginning and the present without the passage of internal duration. The universe may be 8 billion years old, but some of its light has never experienced a single second. And if something can exist without aging across the entire history of the cosmos, then perhaps our understanding of time itself is far less fundamental than we think. The universe has an age. We state it confidently, about 8 billion years. That number is not guessed. It is extracted from cosmic expansion, background radiation, and precise measurements of distant galaxies racing away from us. It represents the time elapsed since the hot, dense beginning we call the Big Bang. Time itself, as far as we understand it, begins there. Not just matter, not just light, time. So when someone says, light older than the universe, the reaction is immediate. That's impossible. Nothing can be older than everything, nothing can predate the beginning of time, but that confidence hides an assumption. We assume that age is an absolute property. We assume that when we assign 8 billion years to the cosmos, we are speaking in a universal sense that applies equally to everything inside it. We imagine a cosmic master clock that began ticking at the first instant and has been ticking uniformly ever since. Every object, every particle, every photon accumulating years at the same fundamental rate. That picture feels natural. It feels necessary, but physics does not guarantee it. In relativity, there is no universal master clock. There is no privileged time that flows identically for all observers. Time is not an external background. It is woven into spacetime, and it behaves differently depending on motion and gravity. Each object traces its own path, its own world line, through spacetime. Along that world line, it accumulates what is called proper time, the time measured by a clock traveling with it. That distinction is crucial. Age, in physics, is not assigned by cosmic decree. It is the amount of proper time accumulated along a trajectory between two events. You are as old as the proper time along your path since your birth. A satellite orbiting Earth is slightly younger than the clocks on the ground because gravitational and velocity effects alter its proper time. Two twins following different trajectories through spacetime can accumulate different ages. Age is path-dependent. Now take this idea to the beginning of the universe. At the Big Bang, spacetime emerges from an extremely hot, dense state. As the universe expands, matter forms, stars ignite, galaxies assemble. Over billions of years, complexity grows. We look backward through telescopes and measure light from the early cosmos. We calculate how long ago it was emitted based on the expansion of space and our coordinate time, the time defined in a frame tied to the average motion of cosmic matter. That coordinate time since the Big Bang equals 13, 8 billion years, but coordinate time is not the same as proper time along every possible path. When we say the universe is 13, 8 billion years old, we mean that 8 billion years of proper time have passed for observers commoving with the cosmic expansion, observers at rest relative to the average distribution of galaxies. That is a specific class of world lines. It does not automatically follow that every entity within the universe has experienced that much proper time since the beginning. Here is where the paradox begins to breathe. Light is different from matter. Anything with mass travels on what are called time-like paths, trajectories that accumulate positive proper time between events. Light, however, travels on light-like or null paths. Along such paths, the spacetime interval, and therefore the proper time equals 0. 0 proper time means that along the photon's path, there is no internal accumulation of duration. From emission to absorption, no ticking clock rides along that trajectory. So imagine the earliest light that decoupled from matter when the universe became transparent, roughly 380 zeros, 0 years after the Big Bang. That radiation has been traveling across expanding space ever since. We detect it today as the cosmic microwave background, the faint afterglow bathing the entire sky. From our coordinate perspective, that light has been in transit for nearly the entire age of the universe. But along its own path, the proper time between its emission and its detection is 0. In the invariant description of spacetime, emission and absorption are connected by a null interval. This does not mean the photon existed before the universe. Nothing existed before the Big Bang in our current models. It means that our language of age and duration does not apply straightforwardly to light. We think of age as a universal property, something that builds up simply because the cosmic clock advances. But relativity teaches us that age belongs to world lines, for commoving observers made of matter 13. 8 billion years of proper time have passed since the beginning. For a photon traveling across that entire span, 0 proper time has passed along its trajectory. So when you detect a photon from the primordial universe, you are interacting with something that, in the strict invariant sense, has not aged at all. The emission event and the detection event are separated in space and in coordinate time. They are not separated in proper time along the photon's world line. Now, reconsider the claim, light older than the universe. At first glance, absurd, but behind the phrase lies a challenge to our intuition about aging. If age is proper time, and light accumulates none, then calling it young or old becomes ambiguous. It does not age in the way matter does. It is not carried forward through billions of internal moments. It is connected across cosmic history without living through it. We measure 13, 8 billion years because our clocks have ticked that long. The universe, defined by matter-based observers, has aged 13, 8 billion years. But light that has traversed that history did not participate in that accumulation. In a sense, it transcends the ordinary narrative of aging. It does not remember the past because it does not accumulate past, the phrase older than the universe. Jolts us precisely because it collides with the hidden assumption that time applies equally to everything. Relativity dismantles that assumption. Time is not a universal river carrying all things at the same rate. It is an aspect of spacetime geometry tied to specific trajectories. The universe has an age measured along certain world lines. Light traces different ones. And at the deepest level, this forces a radical question. If something can span the entire history of the cosmos without accumulating duration, what exactly do we mean when we speak of history at all? In the beginning, the universe was not filled with stars or galaxies or the calm darkness of space. It was an ocean of searing radiation and charged particles tangled together in a blinding plasma. Light existed, but it could not travel freely. Photons were constantly scattered by free electrons, trapped in a dense fog where every attempt to move forward ended in another collision. There was no transparency, there was no horizon, the cosmos was opaque, a furnace without windows. Then something changed. As the universe expanded, it cooled. Expansion stretched space itself, lowering temperatures and reducing the energy of particles. Roughly 380,000 years after the beginning, the cosmic temperature dropped enough for electrons and protons to combine into neutral hydrogen atoms. This event, known as recombination, was not dramatic in appearance. There was no thunderous explosion, no visible flash announcing liberation, but physically, it was one of the most profound transitions in cosmic history. When electrons bound to nuclei, they stopped scattering photons so effectively. The fog thinned. Suddenly, light could travel immense distances without interruption. For the first time, the universe became transparent. Those first freely traveling photons are still here. They did not vanish. They did not fade away into nothing. They continue to move across expanding space, stretched to longer wavelengths as the cosmos grows larger. Today we detect them not as visible light, but as faint microwave radiation bathing the sky uniformly from every direction. This radiation is known as the cosmic microwave background. It is often called the afterglow of the Big Bang. We look at this background radiation and say it is ancient, nearly as old as the universe itself. It has been traveling for approximately 8 billion years. That number comes from tracing cosmic expansion backward in time. We measure how space stretches, how galaxies recede, how wavelengths elongate, and we conclude that the light we now detect was emitted when the universe was young. From our perspective, these photons have aged with the cosmos. We imagine them as ancient messengers that began their journey near the dawn of time and have been traveling ever since. The phrase traveling for billions of years feels natural, but physics invites us to slow down and examine that phrase carefully. The age we assign to that light is calculated using coordinate time, the time measured by observers who are roughly at rest relative to the average expansion of the universe. These observers define a cosmic time parameter that slices spacetime into moments of equal age since the Big Bang. In this frame, 8 billion years have elapsed, yet this measurement depends on the clocks of matter, bound observers. Light itself does not carry such a clock. Along the path of a photon, the proper time, the internal accumulation of duration, is 0. In the geometry of spacetime, the interval connecting the emission of that primordial radiation and its detection today is a null interval. That means the spacetime separation contains no proper duration along the light-like path. The photon did not experience the passage of cosmic ages. From emission to absorption, there was no internal ticking. This does not mean that the universe did not expand. It did. It does not mean galaxies did not form, stars ignite, or black holes grow. Those events unfolded along time-like paths, where proper time accumulates. But the photon connecting early universe to present traces a path that does not gather duration. When you detect a microwave photon from the cosmic background, you are receiving a signal emitted when the universe was young. In coordinate time, it has taken nearly the entire age of the cosmos to reach you. Yet along its world line, those two events are not separated by lived time. They are geometrically adjacent. This reframes what ancient light really means. We call it ancient because our clocks have ticked billions of years since its release. We embed the photon into our narrative of duration, but it has not moved through time as we do. It has moved at the boundary where time, for that path, does not accumulate. Now consider how extraordinary that is. The entire history of the universe, galaxy formation, planetary birth, biological evolution, human civilization has unfolded while these photons crossed expanding space. They have witnessed none of it in any internal sense. They have not observed the passage. They have not aged into antiquity. They simply connect one event near the beginning to one event now. The expansion of space stretches their wavelengths. What began as visible or infrared radiation is now microwave radiation due to cosmic redshift. This stretching is not caused by the photon aging. It is caused by the fabric of spacetime expanding beneath it. Even here, our language is misleading. We speak as if the photon is being stretched, as though it were an elastic object experiencing change. But the deeper truth is relational. The metric of spacetime evolves, and the wavelength we measure today reflects the geometry between emission and detection. All of this reinforces the key point. Our idea of age belongs to matter-based observers embedded in cosmic expansion. The background radiation's age is defined by our coordinate slicing of spacetime. If you attempt to assign age based on proper time, the photon's age since emission is 0. That fact is not speculative. It is a direct consequence of the spacetime metric and the nature of light-like intervals. So when we say this is the oldest light in the universe, we must clarify what we mean. It is the earliest emitted radiation we can observe directly. It originates from the oldest visible surface of the cosmos, the last scattering surface, beyond which light could not travel freely. But in terms of experienced duration along its own path, it is not old at all. This forces a subtle philosophical tremor. The universe appears 8 billion years old from the perspective of matter that moves more slowly than light. Yet the radiation released shortly after the beginning has not accumulated that duration internally. It links the early universe to now without spanning years in the way we understand them. The birth of the first light marks a dividing line in cosmic history, a transition from opacity to transparency. From that moment onward, information could flow freely across the cosmos, structures could be observed. Light could carry records of conditions from long ago, but light does not carry its own aging. It is we who age as we receive it. It is our clocks that measure the eons. The cosmic afterglow is ancient in our frame, yet timeless along its own trajectory. That distinction lies at the heart of the paradox, and it reveals that older is not a universal label stamped onto objects, but a property emerging from how we move through spacetime.